There's some people outside still, is it? Are there people outside? Shall I start? So, first of all, tell me how many of you are not tired? How many of you are not tired? Not tired? Wow. You guys are all tired, is it? Not tired, no? So, raise your hands. Not tired? Wow. Okay, I am quite tired today actually. So, okay. So, any questions from yesterday or the last two classes? No? Okay. So, the thing is that if you do not ask me, I will ask you questions, right? Okay. So, either you ask me or I ask you. Okay. So, okay. So, let us just do a bit of recap. So, the first one I said that first class I said that there are these 4 evolutionary forces, right? What were they? Can you tell me? Yeah. Yes. Yeah. Wonderful. One more. Which we did not discuss much, but it was called population structure, which is about migration and things like that, which we didn't discuss. So, fair, very nice. Okay. So far in the second lecture, I devoted time in discussing things with drift, that is stochasticity, and mutation. Okay. So, today we will bring in selection. So, today I want to start selection. I will put in selection first, then I will put selection and mutation, and finally at the end we will put selection, mutation and drift, all 3 of them, and then we will do some simple plotting or whatever intuition you have obtained by looking at the simple things. We will see what we can learn. Okay. So, that is the plan today. Okay. So, let us first discuss this case of only selection. Okay. So, it is similar to what we have been saying, that is there is the zeros and ones. So, let us say now I am not right now I am not even putting drift, no stochasticity. When the model does not have stochasticity, what kind of models they are? What are they called? Deterministic models, right. So, there is no stochasticity in terms of this random genetic drift, that is, but there is a mutation rate and all, but that is not the kind of stochasticity we are thinking of. Okay. So, let us say 0 and 1, and the fitness of 0 is 1, let us say, and the fitness of 1 is 1 plus S. Okay. S could be positive, it could be negative. If S is 0, what is this model? If S is 0, then what happens? Fitness is equal. So, that is a neutral case, right. That means there is no selection then, right. So, this is the type and this is the fitness. So, yesterday I asked you to write down a deterministic equation with mutation. Today I want you to think the same sort of thing, but with only selection. So, I am asking you, write down how does the frequency of the zeros change as a function of time. Deterministically, this is the average fraction. So, yesterday you wrote down for the mutation, how did you say? You said that x0 will be affected if it did not mutate. We have 0, it does not mutate, plus we have 1s and it mutates, right. That is what you wrote down yesterday. Look at your notes, right. Okay. So, today I am not putting right now mutations. I just want to ask about selection. So, what do you think? How do you think the population would change if there is only selection? 0 had fitness 1 and 1s have fitness 1 plus S. What is the effect of selection? What is the meaning of selection? So, what is the meaning of selection? Sorry?
The person will be selected who has greater frequency.
Yeah, that is right. Yeah. So, therefore, how would the frequency change? This is the equation that we have seen like n times in different versions with different symbols. So that's why it's important to write it in different symbols so that you can recognize that, we saw that on Monday, and Tuesday, Wednesday, Thursday, the same boring story. But it's a boring story, but we should be able to recognize it, right? So that's a big hint here. You have seen this boring story already, but in continuous time. So could you tell me? Okay, so I'll help you here. So this one, it's growing, only growth, okay? So how would it grow? Let's ask that first. What's the growth rate of this? I'm calling fitness as the growth rate. So I didn't tell you that, I should have said that. So this is the fitness is the growth rate. So how would this grow? Oh, let me write, okay, x naught. Let's call it f0 and this is f1. Okay, and maybe we can put specific values, but let me not even do that right now. Okay, so this, the fraction here at time t plus 1 is proportional to the frequency before into f naught. Does this make sense? Does it remind you of this bacteria business? Ek ka do, do ka char and stuff like that, right? That exponential growth. Is this exponential growth? Is it or not? Yes, what's the solution of this equation? If I did not put this proportionality constant. What's the solution of this equation? X0? F0 is constant? Yeah. That's not a function of time. F0 is a constant. So what is x naught t? Why?
If f0 is constant,
huh.
x0 t plus 1 is f0. So it will
X naught t plus 1 is f0 into x naught t.
Oh,
Yeah. But even then it is not 0. It will be linearly increasing, no? So tell me this is the dumbest equation. What's the solution of this? Yeah, f0 to the power t. Right? This is this moronic thing that we keep doing all the time. f0, x naught t is equal to? How much is x naught t from this equation? Is equal to f naught right? And then you repeat this, repeat, and that's how he got that, right? So this will be f naught to the power t or t plus 1. So let me write for x naught t instead. Make sense? Yes or no? So if f naught was, if this is that, so I'm not saying it's twice or something, it can have 2 copies or something, that's what it is. So exponentially, f naught is larger than 1. If f naught is larger than 1, it is increasing. If f naught is less than 1, it's decreasing exponentially, right? That was it. Okay? This much is fine with everyone. That's the selection part. Yesterday you wrote a similar thing for mutations. This is okay? But this is like exploding, a number. This is like in 10 generations, is like, if f naught was 2, it's like 1024 and it will keep doubling in case f naught was 2, right? But we want to keep the population size to be fixed. They're either x naught or x1, total sum should be 1, right? So that's why I'll introduce the following. That's why I wrote a proportionality. This much is okay? And because right, so let's put a constant in front. Can you tell me the constant? See, if I did not put that constant in front, I'll get an exponential growth or decay of the 2 populations, right? But I'm saying both are there and the total sum should be 1. So therefore, what do you think C is? At all times this is true. If I add up the 2 types, if I add them their fractions, it should be 1. So what do you think C is? Now this is elementary math, so 1 by? No, do it carefully. 1 by?
1 by f0 x0
Huh? Yeah, very good. Okay, very nice. So this is f0 x0 t by the same constant. Right. Okay. So that's how this population is evolving. In if I have only selection, right? What's the meaning of this denominator? Yeah.
Why are you taking same proportionality constant?
Because I want. So do you want separate ones? I have only one constraint, right? So this is like a probability should be conserved. So that's the one constraint. So I can fix only one thing. Okay. Okay. So let's look at this denominator. I'm going to call it. Okay, C. Let's call it C. It's fine. What is the meaning of this? It's saying the fraction x naught times its fitness plus fraction x1 times its fitness. This is it has a meaning therefore. What's the meaning? What does this object reminds you of? Basic 7th standard math. What is it a definition of? Huh? What is the meaning of this? What is this object? F naught into x naught. Probability of 0 types times its fitness. Probability of the 1 type times its fitness is equal to average fitness. This is the average, right? Fi xi summation object and its probability, right? So this is nothing but the average fitness of the population. This proportionality constant has a meaning. It is the average fitness of the population. So one thing which so fine. So therefore, if you write down this in the discrete time, this is a non-linear equation, because you see you have an x naught here and x naught here, and in time and x1 is equal to 1 minus x naught. So it's a non-linear equation. So I will not do this, but non-linear dynamics enthusiasts, I'll ask you to do it at home, or maybe on Fridays we'll do it. Show that because it's a non-linear equation, in general it should have more than one solution, right? Here you will find that there is 2 solutions, but there is only one stable solution. Okay, so you can figure it out yourself. I'll leave it as a homework exercise. Okay, but let's leave it here. Okay, and as I claim that you have seen this equation 1000 times. So right now it doesn't look like that you have seen it, right? It looks a little strange. So let's just try to make it more familiar by making it a differential equation. Could you help? What would I get here? Minus right? Okay. And now let's take f naught to be 1 and f1 to be 1 plus s. Okay. So here is the sort of physical funda. If the fitness between these 2 types is small, then the change in the fraction will be large or small. If they are very, very different from each other, this guy has a low fitness, very low fitness, the first type has a very high fitness. Will their frequencies change a lot in a short time, or they will change slowly? So I just look in a small time delta t. Would the fractions change a lot in a small time if the fitnesses are almost same, or will they change by a large amount? So S is small, say S is 0.01. S? Not necessarily, this is arbitrary right now. Okay, suppose S is tiny, 10 to the power minus 3 plus, let's say. Okay, so I'm asking, would the change in the fraction of, or okay, here, sorry, ulta, I wrote this other way. Okay, so when the f naught changes, the 0th one changes in a small time, would the change be smooth or would it be in a jump? It is a tiny change, no, this is slightly different from each other. So, fractions would also change only small amount. Okay. So, therefore, when s is small, it is okay, I can replace the difference equation by a differential equation. Okay. So, when s is small, I will write it as dx naught by dt for small s, and I am not doing this, you should do it yourself, and if I did it right, I will get something like this. From that difference equation. Is that equation familiar to you all? dx naught by dt equals s x naught into 1 minus x naught. Does that sound familiar? Sorry? Yeah, this is the logistic equation. This is what I said. You've seen it 1,000 times. Because if I did not have this guy, this last term, okay, that means I did not have a denominator. What would happen? How would this change? How would the x naught increase? S is positive, yeah. No, but you can take it negative also, it will just decay exponentially or something like that will happen. Suppose I did not have this term, last term. How does x naught change with time? Exponentially, that's what you said, no, over there, if I don't put a normalization. So, this is the analog of the normalization here. This is your carrying capacity. This is what you write in the logistic equation. How does the solution of this look like? I want you to plot. I am not asking you to solve the equation, I am sure you can solve it. But could you plot the solution of this equation? If you can solve it and plot it, or you can just look at it and plot. I would like, Malay, did you do this? Did you ask them to plot? No. Okay, so let's do it. So, please plot for me x naught as a function of time. How does it look? Increase, decrease, oscillate, stay flat. What does it do? Feel free to chat, feel free to discuss with your friends and tell me how does it look and explain to me why. हो गया? वाह. I asked Professor Malay, he said no. But they didn't plot, right? You plotted, they didn't plot. So they have to do it now.
That's why we have to discuss again.
Okay. So, you guys done? Huh? Everybody's plotted it, right? So, how does it look? Who will come to the board? Are why are you guys looking away? Come and plot. You. Yeah. Plot it. No, there. Eraser you have? X naught is a fraction, no? X naught is a fraction, so fraction cannot exceed 1. So,
I think this is not showing 1.
No. The top thing. What is that? See, this is x naught equal to 1.
Yes.
So, how can it increase from above 1? X naught cannot exceed 1. So, what is the meaning of the top curves?
Top curves are decreasing.
No, but can decrease from 2? X naught cannot be 2. X naught is fraction. So,
Also, this is not.
like this, huh? It's like this, okay. Is this what roughly everybody has? Increases and saturates. Does it make sense? Yes or no? Half? Why half? Saturates to what? So if S is positive, it will increase and saturate to 1, right? So this is your famous logistic equation. So roughly it's okay. Okay? So I want you to keep this in mind. I'll come back to this in a second. I'll just write down, you can of course solve this in discrete or continuous time. I'll just write down the answer. If you solve it, you will get this. So this one, you know, he drew something like this. You reach 1, starting like this, and saturate. How much time is it taking? So I started with some fraction, whatever is your favorite number, 0.8, 0.2, 0.3, whatever it is. How much time does it take for it to reach 1? Infinite time, right? So it's asymptotically only. It was never going to become 1. But is that realistic? So I have just these two types in a population, right? So you're saying you will never ever become the 0 type. Not everybody will become 1. It will be 0.99, 0.999, 999, and so on. Is that real? I mean, is that realistic? Can it be true? Just saying asymptotically, you will just edge there, but you'll never get to 1. So what's missing here? Discrete population? Not discrete population, finite population. Infinite population. So here the assumption here is, so when you see these things which is going asymptotically, because it's an infinitely large population, that's what I said in the first class. I'm saying there's no drift, there's a population size infinite. Infinite size will take, population will take infinite time to get somewhere. But real life we have a finite population which reaches a point in a finite time. So that's not captured by this logistic equation. So that's another way to say that we have to include stochasticity, we have to include genetic drift. This one is not realistic. Okay? So I'll come back to that after a short while. Okay, so please do keep this in mind, I'll come back. Okay. So deterministic equation, we remember something which we have done before, okay? But now we agree that we have to take stochasticity into account because that's important, interesting, and so on, right? Okay. So how do we do that? It's pretty complicated, no? So now we have selection and drift. So I have a model again in which this your usual favorite Wright-Fisher model in which I have n particles, 0 type and a 1 type. So let me ask you specifically the following question. So question is this: I have a population with n particles, only one of them has fitness 1 plus s and n minus 1 has fitness 1. Okay? So I start with that Wright-Fisher simulation in which I am going to put those things, right? And then evolve this population. What do you think is going to happen at large times? Do you have the program ready? Yeah? It's working, right? Can you show it? Oh, I should have set it up earlier. Okay, we'll see. Otherwise, I think there's some problem in between. Okay. Yeah, what do you think will happen? Okay, and I run a Wright-Fisher. Is this possible? At a long time, after lots of generations. Is this possible? Yes? Okay. But isn't this the fitter guy, the better one? Yeah? If S is negative, you can think this is the lower fitness one. You're saying S is positive. If whether S is positive or S is negative, this kind of thing is possible. Even if S were negative, I can still, okay, let me say it this way. Let me come to this. Actually, that's what I'm going to say a little later. Let me just stick with this one. Okay, so is this okay, right? But this is also possible. We discussed it on the first day, right? This is also possible, right? And I said that, you know, there's a certain chance that I'll get this and a certain chance I'll get this one. So this is one guy in the entire class who is a genius. Huh? Okay? What's the chance that he or she will get, her or his idea will spread into the class? Okay? So that is only a finite chance. Okay? So what is this chance? The chance is called a fixation probability. Probability that one spreads. And this special person may not have been a genius, it might be the idiot. There is a finite chance that that idiotic idea spreads. Okay, that's what I meant by S negative. If S were negative, even then the idiotic idea can spread. There is a finite chance of that in a finite population. Okay? So, I will not calculate this probability because it requires a bit of machinery. It is called a Fokker-Planck equation. So, we will not do that because it requires, you have to set up several things. So, I will not do that. I will simply give you an example and I want you to plot things and work out what is the meaning of this answer. Okay? So, I will give you the answer. Is the question clear? What is pi? Pi is the fixation probability. It's the probability that if I have one special person who could be stupid or genius, what's the chance that that idea would spread in the population of size n? So that probability is a very famous formula in population genetics, and the person who is credited by bringing this Fokker-Planck theory, which physicists use a lot, to population genetics is this person called Mutu Kimura. I don't have the year here, but okay. So, pi, the same S, is given by this formula. 1 minus e to the power minus 2s divided by 1 minus e to the minus 2n. This is a very famous formula. Any PopGen book you open, you will encounter this. And lots of things that it's a very simple formula. It doesn't apply everywhere, of course, but it is very helpful for developing intuition into more complex models. Okay? So, what I want you to do is the following. I want you to fix a value of n, whatever you like, plot pi as a function of s, where s could be negative, 0, positive. So, let us do that first. So, please try to plot this for me. Show me how does this plot look. Pi as a function of s, where s could be positive, negative or 0. Typically, s is a small number. Experimentally, it's like a 10 to the power minus 3 to 0.1. So, don't think of s as 10 or something. Okay? It could be positive, negative or 0, but it's typically of this order. So, fix your favorite value of n and tell me how does the curve look by looking at that formula. Any ideas? So, if S increases, let us say S is positive, and as S increases, do you think the probability would increase or would it decrease or would it remain constant? Would it oscillate? What do you think? Let us focus on the positive S thing, because you know, so it is saying there is the idea of the genius guy is spreading in the class, right. So, if this idea is very, very good, what do you think his chance of spreading is? It is a slightly good idea versus very brilliant idea. Which one has a higher probability of spreading? How do you think this looks like? Okay, 30 seconds for you guys, and then you have to give me some answer. I am not asking you full answer, but some answer you have to give me. Okay? I will wait for 30 seconds. Sorry? S tends to 0, you want to do that? Okay. S goes to 0, okay. So, he wants to do S going to 0 limit. What happens to S? So, we have to take here not S equal to 0, S going to 0. Okay, so let us focus on that. Okay, so he wants to do that. S equal to 0, what happens if you put S equal to 0 in this formula? 0 by 0 form, right? Numerator is 0, denominator is 0. What do we do in that case? Huh? Sorry? Yeah, I think it's La Hospital or something like that it's called, like, okay, hospital, I don't know. Okay, or it's actually just our dumb Taylor series expansion, that's all it is, right. So, if you do that, what do you get? You don't get 1, you're missing something important. What's the chance then? So, let's look at S going to 0. Some people look at, so this bunch, will you look at S positive first 3 rows, S going to 0, last 2 rows, S negative, all you guys. Let's finish this problem. So, S going to 0. What did you get? Did you get 1? What did you get? 1 by n? Yeah. Okay, do the positive side also. Negative S. Come on guys. Okay, come S positive. Alright, come. Just do S positive, come to the board. It's okay, come. Next time I'll call your friend, don't worry. Okay, S negatives, next is your turn. So don't do the S equal to 0, okay, fine. Is it clear to everyone why S equal to 0 is 1 by n? The La Hospital rule or Taylor series expansion. Yeah, S positive. Yeah, pi should not exceed 1, it's a probability. Going down? Okay, fine. Is this okay? Does it make sense? Roughly qualitatively? So, he is claiming that when S is positive, as you increase the smartness of that mutant, the chances of fixation are increasing, and at some point this guy who is really infinitely smart is definitely going to fix, is definitely going to spread. Does it make sense? So, super genius guy is definitely going to spread, but if it is not super genius but genius, that chance is smaller than 1. And as S increases, the chances increase. Guys, does it make sense physically or biologically or whatever? Okay, negative guys, S negative. What? You want to come? Come. S negative, plot it. It remains a constant for S negative? No. So, think about it physically, right. So, this guy is like a real idiot. What is the chance that you guys will listen to him or her? Will you listen? No, you won't listen to that person, right. So, therefore, the chances of spreading the idiotic idea are small, but this formula actually tells you how small are they. How small is that probability? It's exponentially small. So, let us do this bit of math. So, S is negative. So, I will write it as 1 minus e to the power minus 2 plus 2 because minus mod S. Okay? So, it's 1 minus e to the power again plus 2 and mod S. Right? So, what is this? E to the power minus 2 and mod S. It's exponentially small. Right? So, it's like this. It's going to decay very fast. Okay? On the other hand, you have this probability. So, this is not quite this. It increases linearly and then as S increases at very large values which are not really biological, but it will tend towards 1. Okay? So, there is some shape of the curve. So, what? Right? So, I had told you in the coalescent theory lecture that it is important to realize in the character of these theories is you do not get n separately or mu separately or s separately. Here again you see uses s, but the parameter which is controlling which side you go to is n times s, is a product of these parameters. Okay? So, when s is positive and ns is much larger than 1, then you get this curve. Okay? This is called a selection or the strong selection limit. So, when we say selection is strong, what does it mean strong? Strong relative to what? I am sure I am stronger than somebody, right, but there is somebody who is stronger than me. So, it is relative to something. So, when we say something is strong, selection is strong, it means the selection, this object S is much larger than 1 by n. Okay, that is the meaning. So, every time people ask, oh, how large is your population or how much is selection coefficient, but that is silly. I mean, they will say, oh, is the selection strong, but that is not the point here. It is relative to something always. Okay? That is a scale in the system. So, this is called a strong selection. And what this says is that even if the selection is strong, the chances of a good mutation to spread is not 1. A good guy is not definitely going to win the race. He or she also has to be lucky. So, that is what is stochastic drift, if you like to think like sort of sociologic, sort of social analogy if you want to give. So, this innovative idea has to get also luck, should have an element of luck in order to spread. Okay? So, this probability of a good guy to win is not 1, it is strictly less than 1. Okay? On this side again you see it is a bad guy, it is a dumb idea, it is a stupid idea, yet it can spread in the population. Probability is small, but it is non-zero. Okay? And this is called this is also strong selection, but this is good mutation, this is also weak, this weak mutation. The bad mutation. This in between region is when ns is less than or of the order of 1. So, yesterday we talked about, day before we talked about neutral case. I said put s equal to 0. S is not equal to 0, it never is. But what we actually mean is this nearly neutral. That is, the advantage of this mutant is smaller compared to 1 by n. So, it does not really make sense to have these things saying that it is 0 or something. It is relative to 1 by n. 1 by n is a measure of the drift. Stochastic, so therefore, the advantage is negligible compared to drift. That is what we mean. Okay? So, this is the neutral or nearly neutral case. So, some of the things that you learned about the neutral coalescent theory will go through so long as your S is smaller than 1 or rather mod of it. Okay? So, this is the basic funda. So, which is very important because we always think of survival of the fittest and hoo-ha. It's not about fittest because there's mutations, and not only that, there's also lucky, being lucky. That is the drift. Okay? So the good guy is not definitely going to fix, bad guy can fix. Okay? And then there is this part in which the probability is of the order of 1 by n. Okay? Okay, so that was the sort of simple thing I wanted to say here. But this was with respect to S. There are two parameters. There's S and N. The next job I want to give you is to ask you, how does pi change with N? So please plot for me. How does pi change with respect to N? So here you kept population size to be fixed, and here you have to consider 3 separate cases, right? S could be 0, it could be positive, it could be negative, but N is changing. How does this formula look? Please plot. So you can fix a value of S and imagine fixing a value of S and then changing N. Let's take S positive. How does this look? Again, the first 3 rows S positive, I'm going to ask somebody who has not been to the board at all, okay? And the last 2 rows S equal to 0, and you 3 rows S negative. And the ones who are sitting really at the back. Okay, I'm going to give you a more tougher question. Ready? Anyone? S equal to 0? It's not a long calculation, guys, come on. Huh? How does it look? S equal to 0. You told me the answer already, right? S equal to 0. S equal to 0? How straight line? Pi is, how much is pi for S equal to 0? No, 1 by n. Okay, so I will do the job. This is 1 by n for S equal to 0. S positive, S negative. Answers are all there, no? Okay, okay. So it's decreasing with n, right? So the probability, if I fix a value of S, the probability of fixation is decreasing as n increases. Does this make sense? Can you rationalize this? So I'm saying I have a box with lots of, this is this class with 30, 40 people, and in which is a good mutant. The chances of its fixation are something, but if I have 100 people in the class, these chances of fixation are smaller. That's what this graph is telling you. Does that make sense? 30 people, 1 genius. Idea spreads with certain chance. 100 people, 1 genius. The chances of spreading is smaller. Does it make sense? Yes? Why does it make sense? Explain. Sorry? Unsolved is fine. Ho gaya. That's fine. But we have to see whether it makes sense. Can we sort of physically make sense of this result? Okay, does it gel with our intuition, or does it not? Then maybe we are learning something new.
It is easy to manipulate small.
Okay. Yeah. Manipulate. Okay, right. Yeah. Okay. So he's saying that it's a small population, so it's easier to spread because it has to. I like to think not as a manipulation but fight off. So I'll fight off n minus 1 guys. If they're smaller, it's easier to fight off than a larger population, right? So therefore, chances of spreading are going to be smaller in a larger population. Okay. S positive, S negative, homework. Do it yourself, and I'll ask you for tomorrow's tutorial. Okay. Okay, people, everybody is awake now? Okay, so I was just wondering what to do. Okay, let's do this. So I said I will not do this full calculation, but I'll do a smaller part of that calculation simply because it's very intuitive and it's something again which you don't read in your usual textbooks. Okay, so it's again, I mean, but if you study something on stochastic processes, you will go through it, and it's a sort of smallish calculation. So let's do it. So this is to calculate this fixation probability, but only for beneficial mutations. And this stochastic process which we can use to calculate it is called a branching process. So I'll give you the simplest version. It's known like since the, I don't know, 60s, 50s from a person called Harris and there are other people also. Okay, it's a very standard calculation and it's also relevant for those who are studying infectious diseases. Okay, so we'll see. So again, you know, this is an infection that happens and then it may or may not spread. So that is modeled again using a branching process. Okay, so let me go take you through this calculation in a very simple setting. So what I have in mind is that there is this population dot dot dot. There is a large population with fitness 1. Very, very large population with fitness 1, but there is just single mutant with fitness 1 plus S, and this calculation can be done only provided, I mean I will show you why, but basically it will hold only when S is strictly positive. So I can't get this n dependence and all. For that you have to set up this Fokker-Planck equation. Okay? So there is an n. There are lots of this million individuals which I am denoting by dot 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 because I really don't want to look at them. Okay? And in that, this blue guy, which is what I want to track, appears. So by mutation. Okay, I said only selection drift, but I am assuming that today by mutation one of this guy appeared at a generation t. Okay, so initially there was no this blue guy, and then at some time t a mutation happened and just this one guy appeared. There is a very low chance of mutation, it's a pretty small. Okay. Then what can happen? So we want to write down a recursion equation for this pi. So I am not sure if you have seen these kind of equations. So let us just do it. I mean it's very straightforward. So let me see. Yeah. Let me draw it here. So this one. So let's see what can happen. What can happen is that it had no, so this one in the next generation reproduces itself. It dies out, it has 0 offspring. That's a possibility, right? So I'm saying that I have a generation t, this one guy appears, and what can happen at t plus 1? Let's just list those possibilities and then we'll write down what is called a recursion equation. So let's list down these possibilities. So what can happen is that this guy had no offspring, or it had 1 offspring and so on, or maybe 2 offspring and so on. Okay. So let's say let Pn be the probability, I'm not sure if this is visible, probability that the mutant produces n offspring. I want to calculate pi, which is the probability that the mutant spreads but it's easier to calculate, to write a recursion equation for the complementary probability, which is E, which is the extinction probability. Mutant dies. How are these two related? Pi and E. Last bench, you. Pi and E, how are they related? No, we don't need to know PopGen for that. Pi is a probability it mutant spreads, pi and E is a probability it dies. What's the relationship between these two? Huh? What is that? Yeah, pi plus e is equal to 1. Either you die or you live, right? So this is equal to 1 minus pi, right? So I want to write solve for this guy, but it's easier to write things for this e. Okay, so let's go slowly and write it. So what's the chance of this? So I want to write the probability. So let me qualify this a bit more. It's ET is the probability that the mutant produced at T dies. Okay. So what can you do? So that ET is equal to a sum of these terms. Let me go slowly for this. So it's the probability that the mutant appears at time t and eventually that's dead. So dies eventually. Sorry, I should say it more clearly. Okay. So it's dead here, right? It did not produce any offspring in the next generation. So what's the chance that it did not produce any offspring? Sorry? No, it's P0. It did not produce any offspring. It produces n offspring. So P0. So this is this P0, right? Right? Plus, what else can happen? It produces one offspring, which is this. But this offspring, then I have to ask, oh, what about you? Are you going to be dead or you will have offspring? So that's where this recursion equation business comes into play. So here I am going to say that it's as if this guy is produced at t plus 1 and from here onwards it will have its own trajectory. It will have 4 offspring, 3 offspring and eventually all of them die. Let me explain this a bit. So here I am saying, to write the recursion equation, I am saying let's say this guy produced 1 offspring, that produced maybe 2, maybe 3 or whatever, but eventually all these lineages died. Okay? Let me write the answer. Then I will write it as the probability that this is produced and that times the extinction probability ET plus 1. So from here onwards, you think as if it's a mutant produced at t plus 1 and whatever is that probability is the same probability but starting from here. That's the key point here. If you understood this much, then it's very easy. Is this much okay? Yeah, I'll say it again. So I'm saying here we want to write down, we don't want to ask that, okay, what happened at t, you had one child, now tell me what happened at t plus 2 and so on and so forth. You don't say that. If you want to write a recursion equation, you want to relate things at t and t plus 1. That's the idea here. Okay? So how do I do that? I am saying that one offspring is produced. Okay? So this is like as though the guy was produced at t. The same probability, extinction probability here was ET. So now you write the same extinction probability but at t plus 1. It has the same kind of probability but of a mutant which is produced at t plus 1th generation. Okay? T I am going to take out in a few minutes. Okay? Plus, what will happen for this guy? It had how many offspring? 2 offspring. So what should I write here? P2 and then? ET plus 1. ET is the probability, ET plus 1, yes. It's a probability of a mutant. So 2 means 2 ET? 2 ET plus 1? No. Both should die. Square. Both should die. This should happen and this should happen. P square. Right? So both the lineages have to die. So this guy dies eventually. This guy also dies eventually. Right? So E square. Now it's easy peasy. Next one. What do you think it is? Next turn. P3, same thing, right? P3, ET plus 1 cube and so on. It's an infinite series, right? That's all. That was a sort of basic thing. Once you have gotten this, you're basically done. Is this much okay? Okay, write it here. Okay, so that's the recursion relation. Et equals summation okay. So 0 offspring, it's dead anyway. 1 offspring, it dies, but saying that it's the probability from t plus 1, the same object but at t plus 1 and so on, right? That's all. That's a recursional equation. So it relates, why is it called recursion? Recursion means what? It relates the time t plus 1, the sort of thing we were writing at the beginning of the class. But this is very complicated. It's Et and it is related to t plus e cube, e4, e5, everything. This is extremely complicated equation. So first thing I'll do is to remove the t dependence, saying that I'm interested in some stationary probability. So as I said yesterday, that means t drops out of the picture. Is this simpler? Or more, is it still complicated equation? Is it linear, non-linear? What kind of equation is this? It's very non-linear, right? E to the power 100, a million, everything is there in this equation. How many solutions are possible? Lots of, I mean, we probably think it will be at least one, I mean, of course, but probably more than one. Can you guess one solution of this equation? There's one trivial solution of this problem, of this equation. It has many solutions because it's a non-linear equation. Can you guess the trivial solution? The giveaway is the word trivial. Square? If E is 0, that is satisfied? No. No? P0 is P0 also. So if E is equal to 0 solution, if I put it on both sides, I should get 0 equals to 0. Is that what I'm getting? No. So E equal to 0 is not a solution. What's the trivial solution here? Just stare at it. Huh? Somebody said something? E equal to 1. Why is that? Yeah, very good. Because we know summation Pn should be 1. Right? That's normalized. Right? So therefore, if I set E equal to 1 on both sides, I get indeed 1 equal to 1. The trivial solution here is E equals 1. Okay? So one possibility is that it definitely goes extinct. Right? That's what you would have thought, no? Is one guy is to fight off these lots of them, it will go extinct. Right? That's what you expect intuitively. So what, it's better, but it has to fight off all of them. That's what you guys told me, that n is large, probability is extremely small. Right? So that's what it's saying. Extinction probability is 1. But that's not the solution we are interested in. We are interested in a non-trivial solution. Okay? Okay. So we will do that using what is called a graphical method. So we will again do some plotting and stuff and figure out the answer. Everybody knows what's a graphical method of solving an equation. Suppose I ask you, solve this equation. X equals e to the minus x. Do you know how to solve it? Huh? Yeah. And then? Wherever they intersect is a solution. That's called a graphical method of solving these kind of nonlinear or transcendental equations. Okay? You plot both the functions and wherever they intersect is the solution because that's where they are equal. Okay? So we'll do that here. Okay, so plot. So let's look at our equation again. Okay. So it's useful to take, first of all, this is equation number 1. And I need one more equation which is simply a derivative of it. Let's take a derivative with respect to E on both sides. So 1 equals P0 goes away, and then I have a P1 plus 2 P2E right? Did I do it right? 1, yeah. So for brevity, let me call it g of e, some function g of e, because I want to plot this object. Okay, so not that, I want to plot this object, which is the derivative. Okay. So we don't know Pn, I have not given you Pn, and E is what I am trying to find out, right? So I want to plot this equation, g of E equals 1. What is g of 1? G of 1. Do you recognize it? So you guys recognize that, right? The summation Pn should be 1. G of 1 should be, what is g of 1? No, g of 1 is not 1. Huh? Expectation of? Average number of offspring, average n, very nice. Summation n Pn, 0 to infinity or 1 to infinity, does not matter, is simply the average number of offspring produced per generation. Okay? So I am going to call it mu. Okay. So let us start. So it's the probability. So test will happen between 0 and 1. Okay? And there is some g of 1. Equals mu, right? Let us take the case when we have mu larger than 1. So it's useful to do that, we'll see. Okay? So mu is larger than 1. So this is 1 here. Sorry, mu is like, let's say call it, let's say 2. Okay? Somewhere here is 1. Okay, so I have told you that you know where the things might lie. How do you think this g of E versus E look like? E is positive, right? It lies between 0 and 1. How do you think g of E change with respect to E? Sorry, g? Decrease or increase g of E? 1 to 0 decreases, but let us say 0 to 1. 0 to 1, it increases, right? Why is that? At E equal to 0, the point is P1, yes? Yeah, that's P1. Sorry? Yes, so that's P1 at E equal to 0. Yeah. Yeah, very good. So she is absolutely right. So she is saying, because you know that's what I told you that g of E is 1. So she is using that information. G of E is 1, so it has to become here. This much, and this also she knows. So remember, that's what I said yesterday. When we have to do plottings and when you do some complex models, very nice thing to do is to take the limits. Take this dumb limits and we say, oh, it's not physical, biological, chemical, whatever, whatever. But you know, that's how you learn. You just take these extreme cases and then you fill in the gaps. Filling the gaps is always a harder part. But you get a lot of intuition by looking at these limiting cases. So always do that. Okay? So g equal to 0 is P1, she's right, and g of 1 is E. What happens in between? It's not so hard in this case, so you should tell me. So you said increasing, why? It could oscillate and go. What do you think? Why is that? It's there, I mean, in front of you. You don't need any extra information. P1 plus 2P2E plus 3P3Q E square plus and so on. So as E increases, what happens? It should increase, right? P's are all positive, E's are all positive. So as I increase E, what will happen? Oh, I'm sorry. Yeah, sorry, thank you. Yeah, you're right. Yeah. So he's pointing out, very good. The g of 1 should have been mu, no? So that I made mistake. Okay. So this one, convince yourself, is an increasing function. Okay. So something, I don't know. So g of e looks like this. And then we want to solve the equation g of e equals 1. So this is g of e and this is 1. So all of you told me that you know the graphical method. So what do you think is the solution of this equation? Where is the solution? I want to solve this equation, right? G of e equal to 1. This is a g of e function. Yeah, this one. This is the cut, right? This is the solution of this equation. I don't know yet what it is, but I'll come to that. So there is a non-trivial solution exists. What is it? I'll come to it in a second. If mu was larger than 1. Okay, so I told you this answer when mu was larger than 1. Could you repeat this exercise for me and tell me what's the answer when mu is less than 1? Same idea, plot the same kind of thing and tell me what you find. This time mu is less than 1. How does mu less than 1 differ from the first curve? It probably still increases, right? That's not a trouble. So what's the trouble here? What's the difference? I mean, it's just copying this 2 over there. Only thing that I have done is to shift mu from top to below 1. That's the only difference between first figure and the second figure. But it changes things drastically. So I want you to tell me what is it? What happens? E equal to 0 is P1, that's fine. Yeah, that's okay, that's fine, sure. Okay, let's say less than 1. Let's say less than 1. Yeah, oh, sorry, yeah, let's say less than mu. It's not it's fine, it's not so much problem. The thing that we have to do is something else. P1 is less than mu. Can you tell me quickly? What's the difference here? How does this curve look? It again increases from P1 and then increases towards mu. Over here. And then it can still increase, no? And intersects. So what's the solution? Flatness, okay, right. So okay, so flatness something happens. Okay, doesn't matter. So what's the solution in this case? This point? Does this make sense? Huh? It makes sense? Tell me why. Tell. Why is that okay? Anybody else? So solution is for E, that big white dot. Why is that okay? First order question is it okay or not okay? If it's okay, why is it okay? Huh? It's not? Why? E is probability, yeah. So I cannot have a solution above 1, right? So this solution is invalid, right? Yeah, so that's why P1 should be less than mu. What's the question?
But how can the summation of NPN can be less than 1?
Let's say P2, P3 all are 0. Let's say P1 and P2 are non-zero, P3, P4 are all 0, and P1 is less than mu, like I drew here, and therefore you can find P2 and make sure that it's less than 1. You will have 3 variables in fact, P0, P1, P2.
Suppose we make E equal to 0, when equal to 0, then P1 is equals to 1. So in this graph, P1 is less than 1.
P1 is always less than 1.
But if we put E equal to 0 in the expression of G,
Huh?
then it shows P1 equals to 1.
No, that's not a solution. What we are solving is G of E equal to 1. Right?
How actually you figure out the position of P1 in the first graph?
Okay, you don't like that? Okay, but that's not really the issue. You don't like it? Okay, fine. I just took for simplicity. You want this one? You want this P1 higher than mu? Okay, how will this curve look? So then what will happen in this case? It should reach where? It should reach? So it should reach over here, right? So it should go to here and where does it intersect? You think it intersects here? What's the solution here for mu less than 1? No, not negative, no. Shall we take it up tomorrow for a tutorial? I think what you're saying is okay, but we need to see this a little bit more carefully. Okay? So shall I take it up tomorrow in the tutorial? So you have this point about whether P1 should be less than mu, or why did I choose that, right? That's the question.
No, madam, not P1 is less than mu. My question is when E equals to 0, then P1 is supposed to be equals to 1.
No, we are not solving that. G of E should be 1. That's not a solution. That you are saying that E equal to 0 is a solution. E is equal to 0 is not a solution of this equation. No, that's not what is correct. Some of you are asking about why is P1 less than mu. So that's a separate question. Okay? No, that is not correct. Okay? Okay, so let me just wind it up now. Okay. Yeah. Okay. Okay, so shall I just move on a bit? Okay? Okay, so what have we learned here? Mu equal to 1 I did not do, but for mu larger than 1 there exists a non-trivial solution. For mu less than 1 there is no non-trivial solution. Okay? And you can verify mu less than 1 means S being negative. Okay? The deleterious mutations I cannot address from this framework. Okay? So let me just stick with the non-trivial solution for a second. So what is it? So it says solution is given by this. Okay. So we know that if mu is larger than 1, solution exists. Shall we discuss that afterwards? Okay. So let's come back to that equation again. So what we learned from this graphical method is that solution, non-trivial solution exists only if mu is larger than 1. Okay, that's the sort of bigger result. So E equals to this one. I haven't still told you what is E. So now I'm going to make an assumption, namely that for Wright-Fisher process we had a binomial distribution for the offspring, but it can be approximated by a Poisson process, by a Poisson distribution. Okay. So there is this NP being finite. In that case, it's the Poisson distribution, and the mean is mu. So Pn, I'm assuming, is a Poisson distribution with mean mu. Okay, and I just plug it in. And what happens then? E equals so mu E ooh, there's a big sum to do. Can we do it? We have to solve this 0, 1, 2, 3, so many terms. What is that sum? Can we do it? E to the power? E to the power e mu. Right? Very complicated equation, right? So, it is saying the quantity of interest E equals e to the power e. Wow. Okay, or pi okay, provided mu is larger than 1. So, this you have to solve graphically. Oh, sorry, I should have, mu is just the average, so do not confuse it with mutation rate, sorry. Okay. So, this is the equation which you have to solve graphically, numerically, but assuming that pi is small and pi is small, you can expand it. Taylor series expansion of this, and you should be able to show that pi turns out to be approximately 2 times mu, mu minus 1. So, if mu is 1 plus s, pi is equal to 2s. So, this is a very famous result. It was obtained by this person called Haldane. He spent many years in India, near Bhubaneswar, I think. So, this is the famous result by Haldane, 1920 something. Okay, forgot the year. Okay. Anyway, so 27, yeah. Okay. So, what it's saying is, if I have a very large population, very large class, and there is a special genius guy, his or her ideas are likely to spread with a probability just the twice of the advantage or the innovation it offers relative to the background, relative to the rest of them. Did you see this formula today? 2s. Did you get this? I wrote some complicated formula, right, with s and n and what not for the Kimura formula. Does it have anything to do with it? This pi equal to 2s. Earlier I wrote 1 minus e to the power minus 2s. Are they connected in some ways or not? This was also pi. This is also pi. Are they connected? Are they related in some ways? Sorry? Yeah. 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 S to be small? Yeah, very right, you are right. So, he is saying that, so that means that formula is a special limit of this general formula. So, if ns is very, very large, you can drop this term and expand for small s, you get 2s. So, Haldane's formula is of course is contained in Kimura's formula, which is more general. But extending Kimura type calculation to more complex model is almost impossible. Okay, so, the reason I wanted to introduce branching process to you is because this is one way it is possible to make analytical or even numerical progress to calculate these fixation probabilities. Okay. So, let me just spend 2 minutes asking you. So, I spent this saying that fixation, probabilities, you have to calculate. But what is it for? What do I use it for? Why is it important? It is important, this is the way we take genetic drift into account. It is a building block of stochastic models. Okay. So, let me demonstrate that. So, one last thing I want to do is to calculate a very simple model using this little result 2s and calculate the speed of adaptation. So, remember I said in the first class, what do you think evolution, the speed of evolution is? Is it a fast process? Is it a slow process? And I said it is relative to something and so on, right. So, but what is the speed? I mean, you know that my car goes at 60 kilometers per hour. At what speed does adaptation occur? Right. So, we can ask this question, it is a very valid question to ask. So, can we put numbers on that? Can we calculate it? Can we check it numerically? In experiments. So, there is this experiment that Lenski has been doing. So, they have a very sophisticated model where they can predict numbers and check experimentally, measure match things experimentally. So, I am not going to that level at all. I will just use this little thing and demonstrate to you why is it useful to calculate these probabilities. How do these probabilities form are a building block of stochastic models. So, let me just do this one last thing today. For the people who are experts in nonlinear dynamics, one question. So, I gave you the solutions, right? There are several solutions. I gave you some solutions. Can anybody volunteer to check the stability of these ones? Maybe Malay doesn't like the stability questions, but I think it's a useful question to ask. It's a nonlinear equation. I gave you some, this E equal to 1 is a trivial solution. Is it a stable solution or non-stable? And then you have to ask about all these other detailed things. Any volunteers? I thought there is a lot of experts here. Come on guys, what is this? Okay, I will ask in tutorial for anybody to come to the board and do it. Okay, so let me just tell you about something else which sort of builds upon this. I don't have it here. So, when I discussed coalescent, I said think of zeros and ones, and then suddenly I said, oh no, this is DNA sequence which is a 500 base pairs and so on. So, therefore, we are now suddenly going to move from zeros and ones to a string. Okay? So, that is a sort of again model I am thinking of, because this is very useful, basic and all, but this is a really that 3-month-old ka toy, right. So, we want to do something a little bit more, right. Okay, so, I am thinking of this model which has the full sequence, and I will give you the Wright-Fisher model if you generalize, not with just zeros and ones, but a sequence of length L, and run it the way you are, some of you have written the program. Then when n times mu, so I am bringing now all the three things, selection, drift and mutation. Let me say it more clearly. So, now all three. But I will do it in this limit. And there is a length of the sequence. So, which is like large. Okay. So, I am not showing you how it works out and all that, but I will just give you a picture. So, I am thinking of a model in which I have this sequence of let us say 500 base pairs, and mutation rate is pretty small. Mutation rate pretty small in the sense of n mu is small. Okay. So, once in a while a mutation happens. So, we have a sequence like 0, 0, 0, 0, 0, and that is the one which is sitting in the population. So, I am plotting the frequency of this, let us call this 0, 0, 0, 0, 0. I will denote it for simplicity by yellow 0. Okay. So, that is 1 of this yellow one. Okay. Okay. So, it is spread in the population, everybody has 0, 0, 0, 0, and then one fine day one mutation occurs, and it is a good mutation anywhere. So, let us use a different color. This is all 0. Okay. So, because it is fitter, right, it can possibly take over this population. So, what happens is this frequency goes down and this was not there, and it appears and takes over the population. Okay. So, it's the 1 and this is the 0's population. Then at some other point of time, yet another one comes, the blue one. Its frequency was 0 at a different time, and that takes over because that's also a beneficial one, and so on. Okay, so that's the process I'm thinking about. So is this the question, is the process clear? I haven't asked the question yet. So I'm saying I have this population with all 0, 0, 0, 0, 0. One mutation occurs because it's a good one. There's a chance, of course, it takes over the population. So that's why the frequency increases. Some of you were asking, what do you want to measure? So this is these gene frequencies, or more appropriately allele frequencies, are what people can measure in population genetics theory. That's what it's about. Okay, that's the quantity of measure as a function of time. Okay, so let's say the orange one came, and then another beneficial mutation came, and the pink one came, and the pink one took over the, so the blue one took over the population, and so on. Okay, so how do you think the fitness of this population is changing? Is the population fitness increasing, decreasing, same? What do you think? So I haven't told you. So the fitness of this is 1. Fitness of this guy 1. Okay, let me just write it there. Fitness is 1. Fitness of this guy is 1 plus s. Fitness of the blue one is 1 plus 2s. Very simple model. So how do you think the fitness of this population changing with time? Can you plot something? Fitness of the population as a function of time, roughly. So let's say this was time 100 and this was maybe time 72 and so on. 172, sorry. Sorry? What kind of step function? So initially fitness is 1. Everybody agrees, right? Because everybody has the same fitness 1. Then what happens? So like at 100 time step, what's the population's fitness? 1 plus s. Then 172, 1 plus 2s. And so on, right? So the fitness of the population is increasing, right? But this was, 100, 172, these are random numbers. At the time at which a mutation occurs, it's a Poisson process again. With the times at which the mutation occurs is also Poisson process with the rate 1 by n mu, or the rate n mu. Okay? So that's why it's a stochastic number. So if I had one more trajectory, it might look something like this. And so on. Right? This yellow one is another trajectory, because stochastic trajectory. So actually, if you have time, we should put up his simulation. Okay? So one can have some such fitness populations trajectory. So if I averaged over all these trajectories, how would it look? How would it look? Something like that, right? It turns out, if you take log of this fitness as a function of time, it increases linearly. Okay? So you take average over all these trajectories, plot the log of that, divided, and as a function of time, it increases linearly, and that's why I'm speaking of speed of adaptation. That is the change of fitness with respect to time. D by dt of log w is a constant. That's what speed is, no? Distance upon time. dx by dt, that's your velocity or speed, right? So here, the speed is the rate of change of fitness with respect to time. That's what we're talking about here, okay? So we just want to write for this very simple model, what is the speed of adaptation? So let's write it down. So it's very easy. So the speed is distance upon time. So what is this distance? What is this distance which is changing? How much is distance changing in fitness space? By what amount? Huh? S, right? 1 because 1 plus S, 1 plus S. So distance travelled is S. What is the time? The times during which the fitness is changing is when the mutation came. And what's the typical time for that? That's the rate, the rate at which beneficial mutations are coming into. And that, what n mu is? The mu is the probability that a mutation occurs per site per generation, and there are n particles. So the rate, total rate that anybody can get mutations. No, this guy, this guy, this guy. So the total rate is n mu, but it's a rate. So therefore, velocity is rate. No, it's the opposite. It has a reciprocal of time. So that rate is n mu. So therefore, it's this time, average time is 1 by n2. So this is distance upon time. Is this okay, or something I missed here? Something important I missed, right? Deliberately, so that you can tell me. What's missing? What's missing here in this formula? Distance upon time, but hint. Look at your notes 5 minutes ago. What is missing in this formula? What's wrong with that very nice picture? Something I missed, no, deliberately, and I want you to point out in that. I said it came, the one mutant came, spread. Another came, spread.
The time when it is coming.
No, that's okay. That's not the problem. This is stochastic. That's why I drew several trajectories. So, good guy comes. Everybody agrees. Yeah, sir. Another one comes. Yeah, madam. Is it like that? Huh? Yes or no?
There will be some time between that.
No, it's not about time. Why should we listen to the sir or madam, right? We won't listen. Innovation doesn't necessarily spread. Right? Yeah, there's a chance. That's what this whole lecture was about. Fixation probability is only a chance that this orange guy took over the population. So you won't see it because it came and oops, it didn't spread. You won't see those innovations. So there's a waste of beneficial mutations. Okay, it came, but it did not spread. This bright idea came, but for whatever reason, because that person was unlucky and that innovation got lost. So those things I have not taken care of in this formula. But that's easy to take care by saying it's a conditional probability. Conditional, the speed will change, the speed, it will contribute to speed, provided these mutations contribute, that is, they get fixed. And what's the probability of fixation? 2 times S. That's what we just learned from Halden's formula, right? So that's it. So 2, 4, some people like 4, something, that doesn't matter. But the point here is it's of this form, n mu s square. So this is, in this very simple model, is the speed of adaptation. Okay? So we don't have, okay, time is already 1 minute up, but let me just say one question. I'll just say one line. This question about speed of adaptation is a very active topic of research. We know some things in more complex models, other parameter regimes, we know something, but not sufficiently. There are still a lot of open questions here. We still not fully understand it. Okay? So there are more experiments and more things to be done. So this is something, if you're looking for a problem, this is one very active area of research. So you might, if you want, I can give you sort of papers to look at. So this is one question that you can, might be interested in thinking about. Okay, I think I should just stop here. So there's a lot of more work done, how the pictures changes. If anybody is interested, I can tell you in the lunch time or any break time.